Swayam Prabha. Digital India. Educated India.
Value of the alpha c in terms of the geometrical parameters of this coaxial cable. Okay, so we found out the method to so this is the how we obtain the values of alpha c and alpha d for a transmission line for any waveguide. Okay, so let us see the case for, so we saw what happens for a lossless transmission line. Now let us see the case for a lossy transmission line. So once again, we start with our expression for gamma, the propagation constant, and Z0, the characteristic impedance. And this is equal to alpha plus beta. Now we can have a complete solution for this. We can simplify this expression and equate it plus j beta and equate it to this expression, okay, and obtain the values of alpha and beta. Now that is something we will do for the case of strongly lossy lines. Okay, so once again the differential element, if we draw this with me for completeness, these two combine form y delta z, and these two combine to form z delta z. So we can have a following cases: low loss lines. Low loss lines is a special case for the lossy transmission line, and in this case the values of R and G are small. Okay, if these are small, then what we can do? We can simplify this. So let's start with alpha plus j beta, giving as R plus j omega L multiplied by G plus J omega C. Okay, so we can take J omega L common from here. So this will be like 1 plus R on J omega L, and this will be um, 1 in this whole multiplied by J omega square root of LC. Okay, so now this is equal to J omega square root of LC into 1 plus R upon J omega L half 1 plus G upon J omega C half. Now since R and G have a small value, if we expand binomially these two expressions, we can limit it to the first term. So this will be and then if we multiply this and this, what we get. Okay, now this term we can ignore because both R and G are small, so this is equated to be almost 0. Okay, so we have these terms remaining. Now if we multiply, so we have in this case this term, as you can see, is dependent on G, so this must be equal to alpha D, and this term is dependent on R, so this must be equal to alpha C, and this is nothing but J beta. Now we saw when we have an expression of the gamma like this, that is here beta is proportional to omega, so the dispersion curve that we will get, omega versus beta, is still linear and passing through the origin. So Vp is equal to Vg, group velocity for all places, and is equal to C in free space. So when the losses are less, we see that the propagation through the media is still non-dispersive. Okay, however okay, before going to the strongly lossy cases, let us obtain a value for the gamma if this relationship is satisfied. If this relationship is satisfied, then we have gamma will reduce to j omega square root of LC plus R on C by L. Okay, and Z0 will reduce to R plus j omega L upon G plus j omega C, which is equal to L upon C, and we see that Z0 is constant, frequency independent. So if only we have weak lossy lines, then if the transmission lines are weakly lossy, then we see that it will be non-dispersive, but this Z0 will still be frequency dependent because we have this omega term here. But if we now have this additional condition, which is known as Heaviside's condition, then we see that Z0 will also be, it will remain non-dispersive and Z0 will be real. So usually we want to have Z0 to be frequency independent, like we saw when we were discussing the impedance of a waveguide. We didn't, the impedance, the wave impedance, the ratio between the electric and magnetic field. In one of the previous videos, we saw that for a rectangular waveguide or any single conductor waveguide, the impedance, that is Z, ratio of electric to magnetic fields, is frequency dependent, which was not a good thing. So we never want Z0 to be frequency dependent, but when we have the Heaviside's condition, we see that the characteristic impedance is frequency independent, which is a good thing. Now for strongly lossy lines, we have to do a complete solution of this equation. So we have to actually equate this with this. Okay, so the solution in that case is given like this. So this is the complete solution. I would urge you to once try this solution on your own. So the next important parameter for any transmission line is the power transmitted. So the concept of power comes from the Maxwell's equation, where EC, the complex power that is transmitted through a particular surface, is given by and this we know from circuit theory should be equal to okay. Now this complex power is further can be resolved into two components, the real power PL and in terms of the energy stored in the circuit. So here omega m is the magnetic energy stored in the circuit, and this is WE is the is Wn, not omega m, Wn, and We is the electrical energy. Okay. Now, in terms of circuit parameters, suppose I write a transmission line. So we saw that if Z, I consider at a distance Z, the voltage, say VZ, we know that this VZ can be written as this is, of course, we are assuming this to be a lossless transmission line. So you see, now this component represents a wave, traveling wave. Of course, here we are not including the sinusoidal wave dependence, sinusoidal time dependence. So if we have to write the time as well as spatial dependence, then that will be E of Z multiplied by E j omega t. Okay, the sinusoidal time dependence. Now here in this case, this component represents a wave traveling in the plus z, and this represents a wave traveling in the minus z direction. So instead of writing in terms of e raised to minus j beta z, can I just write it like this? You see that the voltage at a distance z from the source is a sum of two waves, one traveling in the plus z direction and the other traveling in the minus z direction. Okay. So in terms of, so then coming back to our expression for power in terms of this voltage and current, I can, if I write my voltage, the spatial dependence of voltage like this, and the spatial dependence of current like this. Now we know from the equations that we derived for the transmission line, this is actually given by this expression. So our PL, which is equal to the real half of the real of V of Z, I of Z conjugate, can be simply written as Similarly, the value of the imaginary power, that is this expression, value of this expression. So we saw that PC is given as PL plus J to omega Wn minus Wa. The value of this component, that is equal to, so we have J to omega Wn minus We is equal to imaginary V of Z conjugate by 2, okay? And the value of that particular of this in terms of the wave traveling in the positive Z direction V plus, and the wave traveling in the negative Z direction is given like this. One important aspect of transmission line is to account for the discontinuities. So discontinuities are, any abrupt change in a waveguide. So for example, if you have a waveguide which was like this, and then suddenly the width changed like this, is a discontinuity. Right? While this part can be this part can be accounted for as a normal transmission line, and similarly this part also can be accounted for as a normal transmission line. What do you do in this part where there is a discontinuity? So the usual method is to use some lumped elements between these two transmissions. We have a transmission line model for this waveguide, you have a transmission line model for this waveguide, and in between you add some capacitance. So for example, for this particular waveguide, the equivalent model will be something like this. So you assume that there is some capacitance and like that. Similarly, say you have an open transmission line. So in an open transmission line, say there is a central conductor, and you have an outer conductor like this. So these conductors are coming from a distance. See? Okay. So here also you add some capacitance like this. Okay. So in this case, the equivalent transmission line model will be something like this. The blue. So this C is not a part here, just like in this case, this C is not an actual component. We are just adding to this C. We are just adding it to account for the discontinuities. Similarly, here also we are adding this C to account for the discontinuities that exist in this area. Okay. Now, how we obtain the values of C? We can measure it maybe, or best is to use a simulator. So the simulator can you actually find out the S parameters. We shall study what is S parameters in a few lectures. So you find out the S parameters of the waveguides of the complete structure and try to iterate repeatedly the value of this C, okay, so that it matches, so that the S parameters of this circuit matches with the actual circuit. Okay, so this is a model. You want the S parameters of this model to match with the actual electromagnetic structure, so you keep iterating the value of C till you obtain the parameters. Okay. Now, one important aspect that is left for this particular chapter is the concept of impedance. So, I have mentioned that impedance is a real component, and in a transmission line, so say at this particular point, if the voltage is V plus of Z. So this is say this point which is at a distance Z from the source, and say it is at a distance B from the load end, and say the overall length of the transmission line is L. Then and say the load that is connected is ZL. Okay. Then at this point it is B minus of Z. So we have the two waves, the wave traveling in the positive Z direction, V plus Z, and the wave traveling in the negative Z direction, V minus of Z.